located up here on the northwest side in Calallen. And I was asked to give you all a presentation about some soils. And start out, I wanted to just show you my general area here in South Texas. I work down here in the south part. And we also have other soil scientists located throughout the state in each one of these other 4 zones. So just an overview of what I was going to talk about today. I was going to give you a brief history of the NRCS and NRCS today. What is a soil scientist? What is soil and how is soil formed? Then we'll talk a little bit about soil horizons, color, texture, and structure. I also have several videos throughout the presentation that I will share with you on YouTube. We would usually go outside and dig some soil pits and look at color and texture and horizons and all that good stuff outside, but with everything going on, this will give us a little bit more of a visual. I'll continue on with the 12 soil orders. What is soil survey? Who uses soil survey? And then within the soil survey, we'll talk about soil map units, and then web soil survey and soil web are some products that the public can access all the soils information that is out there. And I'll end with some soil sampling techniques and a little bit on soil health.
Excuse me, I'm so sorry. Mr. Hobbs, I'm looking at Kevin Gibbs's face and we can't see your screen. We see your name, but not your screen.
Okay. Let me see if I can fix that.
Okay, so you hit the share screen. Are you sharing your PowerPoint?
Awesome, I can see it, right on.
All right, very good.
All right, which screen can y'all see now? I can see y'all now.
We can see the PowerPoint now.
All right.
And then you just run it like you normally do, Chris. You either click through it or hit the start and run it from the beginning.
Okay.
All right.
All right, are y'all seeing the full screen there? Y'all getting my display screen?
We got you and the screen, so you're rocking.
Right.
Keep going.
All right, so y'all are on the overview page?
Yes.
Good deal. All right, I'll continue on with a brief history of the NRCS. For more than 80 years, the NRCS has been a pioneer in conservation, working with landowners, local and state governments, and other federal agencies to maintain healthy and productive working landscapes. The Soil Conservation Service was created in the USDA by an act of Congress in 1935. However, 1933 should not pass without recognition. That date marks the selection of Hugh Hammond Bennett as the director of the Soil Erosion Service. Creation of the Soil Erosion Service was critical to the future of federal soil conservation activities. The history of the Soil Conservation Service and Bennett's recognition as the father of soil conservation. Hugh Hammond Bennett earned a Bachelor's of Science degree with an emphasis in chemistry and geology from the University of North Carolina in 1903. After graduating, he joined the Bureau of Soils within the USDA. The Bureau had begun to make county-based soil surveys in 1899, which became regarded as an important American contribution to the field of soil science. Mr. Bennett worked outdoors, and he mapped soils and wrote a number of soil surveys. His 1928 publication, Soil Erosion, a National Minutes, influenced Congress to create the first federal soil erosion experiment station in 1929. NRCS today continues to fill the conservation legacy established by Mr. Bennett as it adapts to changing concerns and takes on new responsibilities to address present and future challenges. Through decades of work, Soil Conservation Service and NRCS has developed numerous science-based tools and standards in agronomy, forestry, engineering, economics, wildlife biology, and other disciplines that local NRCS field office conservationists used in helping landowners plan and install conservation practices. Implementing conservation on individual projects contributes to the overall quality of life in the watershed or region. NRCS works closely with landowners to plan and address their objectives. These principles have served well as a foundation for addressing conservation challenges for 85 years and will continue to do so. Next, what is a soil scientist? And where I found this, I don't remember. I've had it hanging on my office wall for years. First, what my friends think I do, they all think I'm in the lab doing experiments. My mom thinks I'm out playing in the mud. And society thinks I'm out here digging for gold. And then my boss thinks I'm sitting on my $8 eating lunch all day. I think I'm out digging in the soil all day, and I'm actually creating maps for our users to use across the country. So a soil scientist studies the upper few meters of the Earth's crust in terms of its physical and chemical properties, distribution, genesis, and morphology, and biological components. Let's see if I can get this video going just to view a day in the life of a soil scientist. Can y'all hear that?
Good.
All right, so there at the end, he was carving up a cloyd and he put it in a hairnet, and that was actually a sample that was taken to send into the laboratory to run bulk density analysis on. That little bucket there was actually liquid saran wrap. And we'll talk a little more about the laboratory analysis of the soil survey later in the presentation. What is soil science? Soil science, did I miss the slide here? Soil science is a science dealing with soils as a natural resource on the surface of the earth, including soil formation, classification, and mapping, physical, chemical, biological, and fertility properties of soils. These properties in relationship to the use and management of the soils. Soils play multiple roles in the quality of life throughout the world. Soils are not only the resource for food production, but they are the support for our structures, the medium for waste disposal. They maintain our playgrounds, distribute and store water and nutrients, and they also support our environment. They support more life beneath their surface than exists above. They facilitate the life cycle of growth and the worldwide distribution of plants, animals, and people. Another video in the life of a soil scientist.
Let's go back and start over because
Yeah. Put your hand over hours a day.
right in the middle.
Hold it with your chin. 3 students. Put your hand right here.
All right, there they were taking a soil core there to do some soil descriptions in a wetland area. All right, so what does a soil scientist do? Soil scientists work for federal and state governments, universities, and the private sector. The job of a soil scientist includes collection of soil data, consultation, investigation, evaluation, interpretation, planning, or inspecting relating to soil science. Aerial photos or various satellite images are often used to research the areas. Computers and geographic information systems help the scientists to analyze geomorphology, topography, vegetation, and climate to discover the patterns left on the landscape. One more video, the life of a soil scientist. Coastal soil surveys seem to be a big push, especially in our local
Just leave that bottom down. Yeah, there you go.
All right, that was a nice soil core they took out in the shoreline, in the ocean. Next, we're going to continue on and talk about what is soil. All right, I know you've probably covered some soil stuff in your class. Can y'all tell me what soil is? Is everybody
Fancy
muted?
dirt.
Fancy dirt? That's something I always discuss whenever I have a outdoor classroom for my elementary and junior high kids. Everybody, I say, what is soil? And they say it's dirt. And I was like, well, no dirt, so it's under your fingernails or what you track in on the carpet. And soil's actually out in the field in place and is alive. So, anybody else?
Breaking down rock.
What was that? I didn't hear. All right, to continue on, what is soil? Soil is made up of 45% minerals, which is clay, silt, sand, gravel, and stones. These minerals is what gives soil its texture. 25% of it is water. The amount varies depending upon precipitation and the water holding capacity of the soil. 25% is air, an essential ingredient for living organisms. Water and air occupy the pore spaces, the area between the mineral particles. 5% organic matter or humus. Billions of both living and dead organisms make up the organic matter. Soil is a product of the effects of climate, biotic activity, acting on parent material as a condition of topography over time. So with that said, can y'all tell me how soil is formed? Y'all covered that yet? What are the 5 soil forming factors?
I don't know.
Okay, we will cover them here.
Chris, we have not talked about soils at all.
Oh, have you not? Okay.
No, you're our second class. We've had a class on botany so far.
Okay.
All right,
All
so
right.
you can feel free to just go to town on soils because they have not learned anything about them.
All right, sounds good. Well, we will talk about how soil is formed. The 5 soil forming factors are: number 1, parent material, climate, living organisms, the landscape position or topography, and time. Soil is a product of the effects of climate and living organisms on parent material depending on landscape position over time. All right, first one, parent material. Parent material refers to that great variety of unconsolidated organic and mineral material in which soil formation begins. Mineral material includes partially weathered rock, ash from volcanoes, sediments moved and deposited by wind and water, or ground up rock deposited by glaciers or other processes. The material has a strong effect on the type of soil developed, as well as the rate at which development takes place. Soil development may take place quicker in materials that are more permeable to water. Dense, massive clay material can be resistant to soil formation processes. Soils developed from sandy parent material, the topsoil might be a little darker than its parent material, but the subsoil tends to have a similar color, texture, and structure. And right here is the 5 types of parent material located here in Texas. Residual, which is formed in place, such as the bedrock. Colluvium is material moved by creep, slide, or local wash from a higher elevation, such as a rock slide or landslide. Alluvial, that's what you'll find down in river bottoms and in the floodplains. They're deposited by rivers, creeks, and streams. And then marine, that's pretty much what we're sitting on here in the coastal plain, is a big marine deposit. And then aeolian, which is the soils that have been deposited by the wind. Next, climate. Climate is a major factor in determining the kind of plant and animal life on and in the soil. It determines the amount of water available for weathering and transporting the minerals. Climate, through its influence on soil temperature, determines the rate of chemical weathering. Warm, moist climates encourage rapid plant growth and high organic matter production. The opposite is true for cold, dry climates. Organic matter decomposition is also accelerated in warm, moist climates. Freezing and thawing, or wetting and drying, break parent material apart. Rainfall causes leaching and also dissolves minerals such as carbonates and transports them deeper into the soil. All right, the next one was living organisms. Plants affect soil development by supplying upper layers with organic matter, recycling nutrients from lower to upper layers of the soil, and helping to prevent erosion. In general, deep-rooted plants contribute more to soil development than shallow-rooted ones because the root channels they create allow greater water movement. Leaves, twigs, and bark from large plants fall onto the soil and are broken down by fungi, bacterial, insects, and earthworms. These organisms eat and break down organic matter, releasing plant nutrients. Some organisms change elements such as sulfur and nitrogen into usable forms for plants. Microscopic organisms produce humus that acts as a kind of glue to hold soil particles together in aggregates. Well-aggregated soil is ideal for providing the right combination of air and water to plant roots. This is an excellent broad ecological region map of Texas, separating the 10 main regions of the state. So looking here on the south, we're on the Gulf, coastal prairies, and marshes bordering the South Texas plains. Next thing that affects soil formation is its landscape position. Landscape position causes localized changes in moisture and temperature. When rain falls onto a landscape, water begins to move downward by the force of gravity, either through the soil or across the surface to a lower elevation. Even though the landscape has the same soil forming factors of climate, organisms, parent material, and time, drier soils at higher elevation are different from the wetter soils where water accumulates. Wetter areas have reducing conditions that will inhibit root growth for plants and require a balance of soil oxygen, water, and nutrients. Steepness, shape, and length of slope are important because they influence the rate of which water flows into or off of the soil. If unprotected, soils on slopes may erode, leaving a thinner surface layer. Eroded soils tend to be less fertile and have less available water than uneroded soils. Aspect also affects soil temperature. Generally, for most of the United States, soils on north-facing slopes tend to be cooler and wetter than soils on a south-facing slope. Soils on a north-facing slope tend to have thick topsoils, and subsoils tend to be less droughty. All right, the last one is time. Time is required for horizon formation. The longer a soil surface has been exposed to soil-forming agents like rain and growing plants, the greater the development of the soil profile. Recent soil deposits by water and wind or soils on a steep slope where erosion has been active may show little to no horizon development. Soils on older, stable surfaces generally have well-defined horizons. As soil age, many original minerals are destroyed. Many new ones are formed. Soils become more leached, more acid, and more clayey with time. In many well-drained soils, the subsoil tends to become redder in color with time. Soil scientists think about all of these soil-forming factors while they are navigating the landscape and during digging. So I've included another video here. I think it was shot in Idaho. So you can think about the 5 soil-forming factors while you look through these landscapes. All right, so while we were discussing the 5 soil forming factors, you probably heard me say horizons a lot. And you notice in the video as they dug the hole, they were driving nails into the soil pit. And what they were actually doing was marking the different layers or horizons of the soil. So we continue on with what are soil horizons? Okay. And let's see here. Soils are deposited in or developed into layers. These layers, called horizons, can be seen where roads have been cut through, hills, where streams have scoured through the valleys, or in areas where the soil is exposed. Where soil forming factors are favorable, 5 or 6 master horizons may be in a mineral soil profile. Each master horizon is subdivided into specific layers that have a unique identity. The thickness of each layer varies with location. Under disturbed conditions, such as in intensive agriculture or where erosion is severe, not all horizons will be present. Young soils have fewer major horizons. The uppermost layer generally is an organic horizon. So organic horizons usually occur in the forested area. It consists of fresh and decaying plant residue from leaves, needles, twigs, moss, and lichens, and other organic material. Some organic materials were deposited underwater. The horizon is dark because decomposition is producing humus. Below the O horizon is the A horizon. That's what we generally see around here when we start digging, is the A horizon, which is mainly mineral material. It is generally darker than the lower horizons because of the varying amount of organic matter. This horizon is where most root activity occurs and is usually the most productive layer of soil. It may be referred to as a surface layer in a soil survey. The E horizon, which is also not included in here, is also in the forested areas most of the time. It is generally bleached or whitish in appearance. As water moves down through this horizon, soluble minerals and nutrients dissolve, and some are washed or leached out. The main feature of this horizon is the loss of silicate clay, iron, aluminum, humus, and some combinations of these, leaving a concentration of sand and silt particles. Below the A or E horizon is the B horizon, or subsoil. The subsoil is generally lighter colored, denser, and lower in organic matter than the A horizon. It commonly is the zone where leach materials accumulate. Deeper underneath the B horizon is the C horizon, or substratum. The C horizon may consist of less clay or other less weathered sediments. Partially disintegrated parent material and mineral particles are in this horizon. The lowest horizon, the R horizon, is bedrock. Bedrock can be within a few inches of the surface or many feet below or not exist at all. Where bedrock is very deep and below normal depths of observation, an R horizon is not described. Okay, so we have the master horizons, and we'll continue on to the sub-horizon. The graph on the right are all the options we have available to us to describe master horizons. I've just included a few here as an example. So we talked about the O horizon earlier, and the subdivisions OA, OE, and OI are used to identify levels of decomposition. An A horizon that has been buried beneath more recent deposits is designated as an AB. An A horizon that has been plowed is designated as AP. The B horizon is further defined by the materials that make up the accumulation, such as the letter T in the designation BT, which identifies that clay has accumulated. Other alluvial concentrations or accumulations include iron, aluminum, humus, carbonates, gypsum, or silica. Soil not having recognizable concentrations within B horizons, but showing a color or structure difference from adjacent horizons is designated BW. Some soils have soft bedrock horizons that is given the designation CR. C horizons described as 2C consist of different material, usually of older age, than horizons which overlie. Differences in horizons is based off the color, texture, and structure within the soil. Another part I didn't mention is the SS part up here. A lot of our soils here in the Corpus Christi area have slickensides in it, and that's from it having heavy clay, and as it wets and dries, it moves, and it'll actually make polished face on the soil beds. So with soil color, if you have a dark soil color, you're usually high in organic content. A light color is low in organic content, and then your red, yellow, and brown soils are well drained. They're generally, the red and yellows are generally due to oxidation of iron compounds in the soil, and reds are highly oxidized. You can compare it to rust on iron. When metal gets wet, as it dries, it oxidizes and turns a reddish yellow color. If you dig a hole and have gray colors, it's probably a sign of excessive wetness, where the iron in the soil is either removed or reduced when oxygen is removed. How do we tell soil color? We look at soil color using the Munsell Color Book. And within this book, there are reds, browns, yellows, yellow, red, grayish browns, and pale reds that are all good descriptions of the soils in our area, but not very exact. Just as paint stores have pages of color chips, soil scientists use a book of color chips that follow the Munsell system of color. The Munsell system allows for direct comparison of soils anywhere in the world. The system has three components: hue, a specific color, value, lightness and darkness, and chroma, which is color intensity, that are arranged in books of color chips. Soil is held next to the color chips to find a visual match and assigned the corresponding Munsell notation. For example, a brine soil may be noted as hue value chroma 10 μR 5.3. The soil color by Munsell notation is one of many standard methods used to describe soils for soil survey. It can be used to define an archaeological site or to make comparisons in criminal investigations. Even carpet manufacturers use the Munsell Color Book to match carpet colors to local soils so that the carpet will not show the dirt or soil tracked into the house. And with that, here's a demonstration in the field of a soil scientist looking at soil color.
For your Envirothon test, you're going to need to determine the color of your soil material. These are two different versions of the Munsell color book. They're both just as good, they're just different generations, but we're going to use the blue one today. Now, the Munsell color book is a standard colored methodology. What we've got are different pages in here with color chips on them. Each page is a different hue, and the hue is identified by a notation in the upper corner. Now, the hue is how red or yellow the soil is. So as you notice, as I'm turning the pages, it was really red to start with, but it's getting to be a little more yellow. And then all the way in the back, it's getting really yellow, almost, greenish colors. So this is one way to organize the color book and orient yourself to which color you should be. One of the things people have the biggest problem with is, where do I start with a soil color book? Now, it's going to depend on your landscape. Universally, kind of the standard is to start on the 10YR page. 10YR stands for 10 parts yellow to 1 part red. That's the Y and the R. Now, here in Utah, we have a lot of really red soils. So looking around the landscape that you're in is going to determine whether you need to start on one of the redder pages towards the front of the book. As we move to the front of the book, this is the 7.5YR page, which is 7.5 parts yellow to 1 part red. As I go even closer further, 5YR is even redder, and then 2.5YR is even redder than that. If we were in a really gray material, perhaps around price, we might end up going the opposite direction from the 10YR page. We might head towards a 2.5Y page, which gets yellower, and 5Y is even yellower than that. They've even taken the R off of it because it's almost pure yellow colors now. So this is the Gley page. When you're in really poorly drained soils, you might use this one, but it's a very particular circumstance. Once you've identified the hue page that you need to be on, you can also take a soil sample to make sure you're where you need to be. Go ahead and break it down so that you have a uniform color in your hand and get it wet. Not soaking wet, but just wet enough that your color doesn't change, because it's going to get a little bit darker once you've gotten it wet. And hold it up against your color sheets to make sure you think you've picked the right one. When you do that, you can kind of just eyeball it and see, does it look like it matches the red tone of this page, or is it a little bit browner and yellower? Do I need to switch back? I can tell that I've gotten the right page because I've checked the ones around it, and the one I started with happens to be the best fit. This one is a little bit redder. So we've identified that we need to be on the 2.5YR page because that's the best color tone match of the hue. That's how red or how yellow your sample is. The next part to identify is the value, which is the up and down number, and the chroma, which is across the bottom. The value is how bright or how light colored the soil is. It's darker brown below, and then it's almost pure white up at the top. So that's the value. The chroma is how dull or how bright the sample is. So you can see these are the really bright oranges, and as we go towards the binding of the book, they're more gray, they're duller colors. So identifying the color tone, we're going to go ahead and try to figure out exactly which chip in here matches best. The way you record the notation is in the same order that you identify things in the book. First, you write down the hue, which is the number up here in the top corner. Then on the value side, you write down that number next, and then the chroma is the last one that goes down. So taking a look at my color book, it's always a good idea to have the light source behind you if you can. You don't want your shadow getting in the way. And then you move it around and try to decide which chip it matches most closely. This sample happens to match the 2.5YR 4/6 chip the best.
Okay, so we all know how to run a color book now. So we were looking at how we decide between different soil horizons. So we looked at soil color, and we'll continue on and look at soil texture. Okay, soil texture is the most important physical property of the soil because it determines the capacity of the soil to retain moisture and air. So what we have here is our texture triangle. And if you look at this, The lines going left and right are your clay percentages. And your silt are going diagonally this direction. And then your sands will go diagonally this direction. So if you have an even mixture of sand, silt, and clay, you'll be here in the middle as a loam. And as your clays go up, you'll go up this direction and so forth. So it is, let me read here. Texture class is one of the first things determined when the soil is examined. It is related to weathering and parent material. The differences in horizons may be due to the differences in texture of the respective parent material. Texture class can be determined fairly well in the field by filling the sand particles and estimating silt and clay content by flexibility and stickiness. In some environments, clay aggregates formed that are so strongly cemented together that they feel like fine sand or silt. In humid climates, iron oxide is a cement. In desert climates, silica is a cement. And in arid regions, lime can be the cement. It takes prolonged rubbing to show that they are clays and not silt loams. So here is a little chart showing the differences in the sand and silt particles. So all these here on the left are your different size sand particles. They're the largest size and they feel gritty. They're low in organic matter and have a whole lot of pore space. And they hold very little water. You look over here on the right, you see your silt particles compared to the sand particles. They're the middle size and they feel smooth. And the smallest particle of all are the clays. They feel sticky, they're high in organic matter, and they hold more water. They shrink when they dry and they swell when they are wet. So this is a chart. If we could be out in the field or outside of the classroom, we would actually go out and do some soil texturing, but I'll go through this chart briefly. To start out, you saw in the videos, you get you a handful of soil and moisten it down and begin to work it, breaking up all the soil particles that you have. And as you wet it, you want to work it to where it's kind of like Play-Doh. So if you start with this chart, you have your soil, and you ask yourself, does the soil remain in a ball when it is squeezed? If not, is it too dry? Have you worked it into a Play-Doh yet? And if you have, it's probably a sand if it won't stick together at all. But if you work your texture sample up and it does stick together, you can continue on and place the ball of soil between your thumb and forefinger, gently pushing the soil with the thumb, squeezing it upward and into a ribbon. Form a ribbon of uniform thickness and width. Allow the ribbon to emerge and extend over the forefinger, breaking from its own weight. If it does barely ribbon and feels really gritty, you probably have a loamy sand. So if you continue with your ribbon and can get one about 2.5 centimeters in length or 5 centimeters in length or longer, it goes into these other categories. So if you can get a little ribbon on there and it feels kind of gritty, you go over as a sandy loam. And then if it feels smooth, you might be a silt loam. And if it's either gritty or smooth, it'll be a loam. So as you're working your Play-Doh ribbon, texture out, like I said, if it gets to be 5 centimeters, you'll come down here, and if it feels gritty, you'll be in a sandy clay loam. If it feels smooth, you'll be a silty clay loam. And if you're neither gritty or smooth, you'll be in a clay loam. And then if you can really make a long ribbon, you can get, some soils will ribbon out several inches long. If it's really sticking together good, and it feels gritty, you'll have a sandy clay. And then if it's smooth, you'll have a silty clay and then a clay. So we talked about soil color, soil texture, and the third thing we look at whenever we're breaking up soil horizons is your soil structure. So this is a chart showing the different types of soil structure. As we talk about the different types, this picture here on the top right is a demonstration of a prismatic structure, which you see here. And this right here on the bottom right will be a demonstration of your subangular and angular blocky structure. So granular, the units are approximately spherical. They have curved or very irregular faces. Blocky structures, the units are block-like. They are bounded by flat or slightly rounded surfaces. The structure is described as angular blocky with relatively sharp angles, or as subangular blocky with a mixture of rounded and plane faces. Lenticular, the units are overlapping lenses parallel to the soil surface. They are thickest in the middle and thin towards the edges. Lenticular structure is commonly associated with moist soils, texture classes high in silt or very fine sands. Platey, the units are flat and plate-like. You can usually find your plate-like structure if you're out in a farm field, which you hope to not find it, but as farm implements go over the soil surface, it will pack down and make a platey type structure. Wedge, these units have acute angles found in high clay soils. They are commonly bounded by small slicking sides. We have a lot of those down in this area. Prismatic, the individual units are bounded by flat to rounded vertical faces. Units are distinctively longer vertically. Vertices are angular or sub-rounded. The tops of the prisms are somewhat indistinct and normally flat. Like again, this picture on the top right demonstrates the prismatic. And then columnar, the units are similar to prisms and bounded by flat or slightly rounded vertical faces. The tops of columns, in contrast to those prisms, are very distinct and normally rounded. Okay, so we talked about 3 different things that we look at to determine soil horizons. And we'll continue on and look at soil taxonomy. Soil taxonomy is a soil classification system developed by USDA. This system is used to describe soil properties and is used worldwide. At the highest level of classification, soil taxonomy places soils into one of 12 categories known as orders. Each of these orders represent a grouping of soils with distinct characteristics and ecological significance. And I have a little video here. It's more of a song that'll tell you the difference between the 12 different soil orders. And here's a map, a generalized map of the 7 dominant soil orders here in Texas.
Here's a little song I wrote for you to help you learn your dirt. Well, they're pretty boring, so to keep you from snoring, I've put them into verse. Well, alpha soil's got great horizons for plants and grass and trees. And the old soils are the reddish clays that you find here in the southeast. Well, septic soils are found in the hills. They're young and they're widespread. But if you play too long on an andesol, you might just wind up dead from volcanic eruptions. Well, the endosols are the least developed. They're found far and wide. They're spread all over steep rocky slopes, but also by the river sides, like in the Louisiana Delta. Well, the iridosols are the desert sands that dry most of the year. And the gellosols are frozen fun, so dig a hole and cool your beer. If you're 21, that is. Well, the vertisols have cracks so big they'll swallow your RV. They got a lot of clay and can ruin your day. They shrink and swell, you see. Well, the oxasols are the tropicals where the rainforest used to be. They're really red and practically low fertility. Well, the histosols are the peats and mucks as dark as a moonless night. They're soggy and wet, you can bet that organic material's high. And the mollusols grow the corn so tall in the Midwest you can't see. Well, they're found all over the Kansas grasslands where the buffalo used to be. Well, the sodasols can grow the pines in the coastal plains back east. They got a low pH, but they're really great if you want to grow a long leaf pine, that is. Well, that's the dozen that you need to know, and I hope you like this song. So when exam time comes around, you get more right than you get wrong.
All right, so that was the 12 soil orders. This next slide shows the dominant soil orders across the United States. You look here along the coast, it has a lot of the vertisols and mollusols up here in the central part of Texas. So now we've learned a little bit about soils. We'll look more into what is soil survey. Soil survey is one of the main tools available to help land users determine the potentials and limitations of soils in a soil survey. Soil survey is available throughout the USDA NRCS. The surveys are made by NRCS in cooperation with other federal, state, and local agencies. Our offices can provide this information, but the soil surveys are also available on the internet. Web Soil Survey allows you to produce a customized soil map for your own area of interest. The original soil survey manuals are available at Web Soil Survey website, but do not contain the most up-to-date information. The soil survey generally contains soil data for one county, parish, or other geographic areas, such as a major land resource area. During a soil survey, soil scientists travel over the landscape, bore holes with soil augers, and examine soil profiles. They determine the texture, color, structure, and reaction of the soil and the relationship and thickness of the different soil horizons. Some soils are sampled and tested at soil survey laboratories for certain soil property determinations such as cation exchange capacity and bulk density. Like any other tool, a soil survey is helpful only if you know what it can do and can't do, if you use it accordingly. The survey does not replace careful on-site investigation or analysis. So within soil survey, there's 5 different orders, starting on level order 1. This is for very intensive land use. This is for areas that are planting specialty crops or experimental plots. Here in South Texas, whenever you pull up a soil survey map, a lot of our maps will be in order 2. They're used for predictions of soil suitability and treatment needs, planning for ag use or construction. There might be some order 3 areas that will typically be your rangeland pastures. Precise soil information is not required. Order 4 is the general land management map for major kinds of land uses and selecting areas for more intensive study. And then the order 5 soil survey is for regional land use. So soil survey starts with dividing landscapes. Landscape classifications are designed to divide landscapes into units, which with significance for the development of conservation plans for natural resources. Classifying the landscape helps to reduce complexity. Areas are divided by similar soils, water, climate, and geology to make management easier. There are local experts who study each area. So we'll start with a map coming up of the United States split into land resource regions, which will be like an order 5 map. Then we'll look at another map of major land resource areas. So as you see here, this is splitting the United States up into different regions. And Then this is splitting Texas up into major land resource areas. Here in South Texas, 150 runs along the coastal plains. You have 83 over here on the west side. So the next question is, who actually uses soil surveys? Soil surveys can help home buyers or developers determine soil-related hazards or limitations that affect home site. They can help land use planners determine the suitability of areas for housing or on-site sewage disposal. They can help farmers estimate the potential crop or forage production of the land. They can be used to determine the suitability and limitations of soils for pipelines, buildings, landfills, recreation areas, and many other uses. Great differences in soil properties can occur within short distances. Soils may be seasonably wet or subject to flooding. They may be shallow to bedrock, or they may be too unstable to use for foundations for buildings and roads. Very clay or wet soils are poorly suited for septic tank absorption fields. A high water table makes soils poorly suited for basements or underground installations. These soil properties and many others that affect land use are given in soil surveys. Each soil survey describes the properties of soils in the county or area surveyed and shows the location of each kind of soil on detailed soil maps. So this is a picture here of what they call a Giddings probe. They can be used to take samples for the top couple of feet. And they can go down to 30 or 40 feet as you hit bedrock. So what is a map unit? We talked about soil survey. What is a map unit? So each of these polygons here, or circles drawn down on this map, is considered a map unit, which is a delineation on a soil map that represents an area dominated by one or more major kinds of soils or miscellaneous areas. Each soil type has a specific range and characteristics or property that it meets. Every map unit is made up of the soils or miscellaneous areas for which it is named and some minor components. The objective of mapping is to separate the landscape into landforms that have similar use and management requirements. The delineation on the map provides information for the development of plans. If intensive use of a small area is planned, on-site investigation is needed to define and locate the soil and miscellaneous areas. So there are different types of map units. These examples here come from Google Earth on the left. You see a consociation map unit. It just has one major soil type. And then here on the right, it'll be an association that has two different soil types. And it'll show you the percentage of those soils in there. Just something to think about when you're looking at soil maps. Official Soil Series Descriptions is a national collection of more than 20,000 detailed descriptions covering the United States, territories, Commonwealth, and island nations. The descriptions in text format serve as a national standard. The name of the soil series is a common term used to name soil map units. These descriptions contain soil properties that define the soil series, distinguish it from other soil series, and provide a record of soil properties needed to prepare soil interpretations. So I have a video here. It's rather long, but it goes through our national laboratory where all our soil series analysis are performed. And this photo here is actually a pit that's being dug and prepped to take soil samples to send to the national laboratory. The shoring equipment's present here on the right to keep the soil from caving in. But I'll let you watch this video and see what goes on up in the national laboratory.
Nature has endowed the earth with glorious wonders and vast resources
that man may use for his own ends. Regardless of our tastes or our way of living, there are none that present more variations to tax our imagination than the soil, and certainly none so important to our ancestors, to ourselves, and to our children. The mission of the Dr. Charles E. Kellogg Soil Survey Laboratory is to measure soil properties that are critical to soil survey and conservation efforts of the USDA Natural Resources Conservation Service and the National Cooperative Soil Survey. Data for these properties contribute to decisions concerning best use and management of soils. Located in Lincoln, Nebraska, the Kellogg Laboratory employs numerous full-time technicians and scientists who analyze thousands of samples annually. No other facility in the world carries out as wide a range of soil analytical methods. Laboratory information serves as the basis for maps showing distribution, limitations, and best use of soils. Soil data and maps are freely available to the public online. The life cycle of a laboratory soil sample begins in the field, where soil scientists describe and collect samples. Reasons for collecting samples include natural resource inventory, mapping, classification, and interpretation of soils, and research projects. The work of the Kellogg Laboratory is carried out in several sections, including sample receiving and processing, chemical analysis, mineralogical analysis, physical analysis, biological analysis, and spectroscopic analysis. Each sample that arrives at the Kellogg Laboratory is assigned a unique number, establishing an electronic audit trail, documenting the handling and analysis of the sample throughout the various sections of the laboratory. Soil samples are first air-dried and then processed by hand. The less than 2 millimeter fraction is called the fine earth fraction. This is the reactive portion of the soil and is the fraction that is analyzed by the laboratory. After soils are processed, they are stored in this room for analysis. These larger containers have quality control samples. An appropriate quality control sample is analyzed with every batch of test samples. If results for a quality control sample are outside established limits, corrective action is taken. After all analysis have been completed, there is a multi-level review process to ensure the quality of the data. In the chemical analysis section, soils are tested for pH, available phosphorus, total carbon, trace metal content, and other chemical properties. Here, an analyst is determining cation exchange capacity, which is a measure of the ability of the soil to hold plant nutrients. The Kellogg Laboratory continually seeks ways to improve methods using new technology and also develops new methods based on the progressive needs of soil science. The laboratory uses the latest technology to maintain a cutting edge in data quality and analytical efficiency. In the soil mineralogy section, soil minerals are identified and quantified. Much of the reactivity of a soil is due to certain minerals, which influence soil characteristics, such as availability of plant nutrients, the capacity of the soil to hold water, and the rate water moves through the soil. Soil mineralogy also influences engineering interpretations, such as shrink-swell potential and suitability for use as construction material. Sand and silt mineralogy is evaluated using a petrographic microscope. Clay minerals are too small to be seen with an optical microscope, so they are identified using an X-ray diffractometer. Thermogravimetric analysis is used to quantify certain minerals by evaluating thermal properties as they are heated to high temperatures. In the physical analysis section, soil properties such as particle size distribution, bulk density, and water retention are determined. Here, particle size distribution is being evaluated to determine soil texture. Texture drives many interpretations and has a significant influence on the capacity of the soil to retain nutrients and water, the rate of water movement, and bulk density. Bulk density influences the penetration and growth of roots, movement of water and air, and the suitability of the soil for various uses. Water retention data are used to estimate plant available water, which is a key factor for predicting native vegetation and the suitability of different soils for agricultural use. There is growing interest in biological properties related to soil quality. Because land management has a significant impact on soil quality, soil samples representing different types of land management may be analyzed for indicators of biological activity, such as soil organic carbon and enzyme activity. Soil carbon in the form of organic matter is an important sink in the global carbon cycle and also influences soil structure, tilth, aggregate stability, and water retention. Soil spectroscopy is an efficient alternative to conventional laboratory methods for the estimation of soil properties. Statistical models are developed from spectra of soil samples that were also analyzed by conventional methods. These predictive models are used to estimate soil properties of unknown samples from their spectra. Research on quantitative soil spectroscopy is continuing and has the potential to improve the efficiency of a range of chemical and physical analysis. Soil scientists use laboratory data to classify and interpret soils for landowners and other stakeholders. Civil engineers use soil survey data when planning the construction of a highway. Laboratory data are used to assess and validate soil conservation practices recommended to farmers to minimize erosion and improve soil and water quality on working lands. Other federal agencies use soil data to assess important ecosystems, such as wetlands. This reflects just a small portion of our customer base. At the NRCS, we understand the need for soil analytical data, and the goal of the Kellogg Laboratory is to help ensure that those needs are met. The Kellogg Laboratory curates the largest soil archive in the world, with hundreds of thousands of soil samples from all 50 states and over 70 foreign countries. These samples represent decades of soil inventory, as well as use of soils data for conservation efforts concerning one of our nation's most valuable and least understood natural resources. Here, for example, is a soil sample from the Houston Black Series. It was collected from Bell County, Texas in 1980. Because these samples are stored in an air-dried condition, little change in their properties is expected. These historical samples and reference data are invaluable for investigation and application of new analytical methods. Research projects benefit from samples with a range of known properties or wide geographic distribution, and may offer the potential to study changes in soil properties over time. On behalf of the National Soil Survey Center, we want to thank you for your interest in the Dr. Charles E. Kellogg Soil Survey Laboratory. If you would like additional information about the Kellogg Laboratory and its mission to support soil survey and soil conservation efforts, please visit us online at soils.usda.gov.
All right, so there's a lot goes on up there at the Soil Survey Lab. So lots and lots of soil samples in that building. So you heard a mention on there, Houston Black soil. They had some samples of there in the archive. Houston Black is actually the state soil of Texas, pictured here on the screen. It occurs on about 1.5 million acres in the Blackland Prairie, which extends from north of Dallas south to San Antonio. Because of their highly expensive clays, Houston Black soils are recognized throughout the world as a classic vertisol, which shrink and swell markedly with changes in moisture content. These soils formed under prairie vegetation and then calcareous clays and marls. Water enters the soils rapidly when they are dry and cracked, and very slowly when they are moist. Houston Black soils are used extensively for grain sorghum, cotton, corn, small grains, and forage grasses. They also occur in several metropolitan areas where they are very high shrink swell potential. Commonly is limitation affected by building site development. The Professional Soil Scientists Association of Texas has recommended to the state legislation that the Houston Black Series be designated as the official state soil. This series was was established in 1902. So next we'll take a look at some of the tools available to access soils information. The first one is Web Soil Survey. As you look, I'll let y'all write these down here in just a minute. If you're looking for Web Soil Survey, you can just type in Google or whatever and it'll come up. What I wanted to point out over here on the right, the National Soil Characterization data, you can go to that and access all the lab data that was produced there from the KSSL lab. If you wanted to pull up soil information of your area, just go to Web Soil Survey and hit this Start WSS green button. Once you get in there, there's several different ways you can navigate to your area of interest. The first one is to use these two tools right here, and you can zoom in to your area. Oh, I lost it. Try that again. You zoom into the area that you're interested in. Or you can also use these features on the left and put in your address. Or you can search by state and county. And there's even a place in here you can search by coordinates. You can just type those in. But you can use this other tool to navigate around. But once you get to where you're going, you can select this area of interest tool and draw a box around the area you're interested in looking at. That will then produce a soil map of your area. And here's the different soil series of this area that we talked about earlier. Once you get that pulled up, you can go over into the Soil Data Explorer, and it provides all kinds of interpretations on the different soil types that you're looking at. So, like I said, that's one feature. That's where all of our NRCS soil data can be found. They replaced the old soil survey manuals that are out and about. Like I said, all the most up-to-date information is here in Web Soil Survey. One of the other deals, if you wanted to, we talked about taking soil descriptions. If you pull up the soil series and want to see what its official soil description looks like, you can go to this other website. And like one we were looking at a while ago is Victoria. Where did it go? There we go. This is the official soil series description for Victoria. Very extensive, but here you have your horizons that we talked about earlier. And then it goes into your color, texture, and structure right here at the beginning. So just a tool you can look at if you're curious what the actual description is. And then UC Davis out in California has been producing a lot of tools. One of these, you can download an app on your phone, and you can actually search by your location, and it'll pull up the soil series that you're actually standing on. Another one of these, you can download and use it in Google Earth. All your soil maps and soil data will be available in Google Earth. And this is one here talking about soil properties is one I just saw come out recently. We'll take a look at it. I haven't used it a whole lot yet. But similar deal with as Web Soil Survey, but you can just take and zoom into your area. And then look at the different properties that you might want to view over here on the left. There, it gives you a visual of the surface soil colors in South Texas. It's a pretty neat tool. Something else you can look at, chemical property, if you want to get an idea of the general pH of your area.
Excuse me, I have a question. On the map where you just showed the general the color of it, would
Yes,
that relate back to the Munsell book, or is that just
that's correct. It does relate back to the Munsell book. What's in the official soil series description? Yes.
right on? Thank you.
Uh-huh. I'm glad somebody's still out there. I was starting to wonder. Let me see if another one here. We saw them take bulk density samples earlier, those cores they were putting in the hair nets. Just the different bulk densities in the area. And like I said, you can zoom in. Let me see if I can get my Google Earth going. I don't know how, I probably can't. But anyway, have y'all had time to jot down these websites?
No, not yet, but I think they're gonna record it and we can go back and grab that stuff.
Okay,
I took
sounds
it.
good.
Smart person took a screenshot.
All right, well, hopefully they didn't get me in there. But, all right, so just some tools there available. Like
I
said, there's tons.
screenshotted it, took the text from the screenshot, copied it to Kevin, and emailed it so he can email it out to y'all.
Cool, thank you.
That's why you're the queen, Beth.
That works. Well, next we'll go on and look at soil sampling techniques. And if y'all want to come back to any of this here, I'll be happy to. Okay. So soil sampling techniques. Whenever you're taking soil samples, you always want to look at the top 6 inches. The most important factor you're going to look at when getting a soil analysis is your pH. Ideal pH is 5.5 to 7.5. Most of the United States ranges from 4 to 8.5. You get up over 8.5, it's probably a salt problem or something else. Roots really do not like living in a high pH soil, same as a low pH soil, which will get acidic. pH meters, they're out there, they're best for testing if you didn't want to send it into a lab. If you get a bad soil test back with a low pH, you can add lime to raise it up, and then sulfur is used to lower the pH. I found that sulfur takes a while to lower the pH in the yard, a year or two with multiple applications. So just remember, plants are only as good as your most limited nutrients. I also always like to recommend if you're taking a soil sample in a garden or a yard or a small area, you want to think about the 5 on the dice and take a soil sample in each of those 5 spots of the top 6 inches and mix it together so you get a good idea of what the whole area is like. When you send your soil samples in, you can tell them the lawn you're growing or the crop, or if you're doing a garden, and if you include the crop or lawn type that you're growing, they should send back a recommendation on fertilizers and other things that might need to be added.
I'm sorry, did you say when you're sampling, you're going to take your soil samples like the 5 on the dice? You mix those all together and then take the sample and test it?
Yes. So you'll lay out your plot, and like I said, you'll collect from like 5 different areas that you're looking at, and you mix all that together, break it up, and you'll just take a portion of that out to bag up and send in.
Okay, right on. That makes sense. Okay, thank you.
Yes, if y'all interested in watching this video on how to take a soil sample, I think this is a guy out in the farm ground.
Sure.
Get it going.
I'm glad you said 5 different areas because I was thinking like a whole dice for real.
Right. Which it all depends on your area. Every spot's a little different.
Do you ever wonder why you need to take a soil sample? Somebody like me tells you need to go out and take one. It's a lot of work. You wonder, why do I need to do that? The reason is that if you're growing crops or plants, you don't know how much to fertilize or lime without the results of a good soil sample. A good soil sample starts with the sample collection, and we'll talk about that in a minute. After you get your sample, you send it to a lab, a good reliable lab, analyzes the soil, gets results. Then research data are used to make recommendations based on these lab analyses. So none of that can happen unless you take a good soil sample. How do you take a good soil sample? First, you need some basic equipment. You can either use a digging implement like this sharpshooter. You could use a shovel instead. And the way you do that is you go down, you dig a little deeper than 6 inches, bring the soil up. Now we only need 6 inches of this soil. So if I take 6 inches from the top, it comes to right there. I then need some tool to stop it at 6 inches, get rid of the rest. Then we need this to be kind of uniform. We want a core, a sliver of this instead of the entire amount. So here now we have a 6-inch sample. We put it into the bucket. That's a fair amount of work. If you're going to take very many soil samples in your life, you would be well off to either buy or borrow a specialized soil sampling probe. Now, a soil sampling probe is not good for anything except taking soil samples. So if you don't plan to take but 3 in your life, it's not worth buying $50 to $100 for one of these. However, if you plan to take many, then this will be a great thing. Sampling depth is critical. You may have noticed I used 6 inches on the last one. The sample has to be taken at a depth of 6 inches for general nutrient analysis. The reason for that is that the nutrients are stratified in the soil. There are more nutrients in the upper part of the soil than there are in the lower part of the soil. So if you take a sample shallower than 6 inches, it'll look like you have a better amount of nutrients than you actually do. If you take the sample deeper than 6 inches, it will look like you have fewer nutrients than you actually do. You may notice that I've made a 6-inch mark with some electrical tape on my sampling probe so that I don't have to guess where it is. So with this, you just push it down into the ground to your 6-inch mark, give it a quarter turn. The quarter turn keeps the soil in the probe when you remove it. You bring it out, you got a nice 6-inch core of soil there. Just put it into your bucket. Whichever way you use, you have to repeat this 10 to 15 times through the field to get one sample. What I just did is not a sample. That's called a core or a subsample. And you need 10 to 15 cores or subsamples to make up one sample. Once you have gotten your 10 to 15 cores and you have soil in your bucket, then you thoroughly mix it with either your soil probe or a stick or whatever you wish. You mix it up good. And unless you like paying a lot of money for postage, you don't want to mail all of this. We need about a pint in the lab. So you use a container that will hold about a pint of soil. And you pour, since it's all mixed up, it doesn't matter if you spill some. Then you put about a pint of soil into this bag, and I have gotten about a half a pint on my arm. So this is your sample. Once you get your sample, we need some basic information on the container that you put the sample in. We need at a minimum your name, address, phone number, what the ID of the sample is, and what crop you're growing. Obviously, we need your name or we don't know who you are. We get quite a few samples in our place that don't even have a name on them. And basically, we just throw them out because there's nothing we can do with it. Then we need your address so we know where to mail your results to, or your email address at a minimum. Then we need to know, or you need to know, what this sample is called. If you send in more than one sample, you have to differentiate them some way, or else you're not going to know which sample is which if they have different fertilizer and lime recommendations. Then we need to know what crop you're growing so that we can make fertilizer recommendations. Can't really make a fertilizer recommendation on an unknown crop. Our recommendations are very specific to a crop and vary depending on which crop you are growing and also what yield goal you have. So if you're after a particularly high yield goal, or if you're a particularly low input person, we need to know that so in order to make a good fertilizer recommendation. Now then, let's say that you have a field that has a lot of odd spots in it, or even one odd spot in it. Say there's an area in this field that doesn't grow anything. You don't want to include that area in your sample. If you do, it'll just make the rest of your sample look a little bit worse, and you won't know why the bad area is bad. So sample that bad area separately. And the way you do it, if it's just an acre, you go out and you take soil from 10 to 15 places at random, just like you would in a regular sample. If it's an area where you feed hay in the winter, you would do that separately because it's likely to be much higher in nutrients than the others. And if you include it, it's going to make the rest of your sample look much better than it actually is. So problem areas or odd areas, sample those separately. When do you want to do this? It really doesn't make a lot of difference as long as you do it at the same time each year. Your soil pH and phosphorus and potassium levels can vary fairly greatly depending on what time of the year you do it. So if you begin your sampling in the spring, try to sample in the spring every year. If you begin your samplings in the fall, try to sample in the fall every year. That way you will have a consistent background on which to compare your soil from year to year. How often do you need to sample? Generally, if you're looking at just phosphorus and potassium and pH, probably every 3 years is enough, unless it's a very unusual case. However, if you're looking at nitrate nitrogen, then you need to sample that probably within 30 days of when you're going to apply the fertilizer, and then that analysis is only good for that year. Nitrogen is very dynamic in the soil. It changes forms. It's taken up by the plant and used. It can be lost in heavy rainfall. So nitrate nitrogen analysis are only good for a couple of months. pH, P and K analysis are probably good for several years. So basically based on that, a good soil sample can give you a basis on accurate fertilization. However, you need to take the sample correctly. Taking the sample correctly involves sampling to a 6-inch depth, no more or no less, taking 10 to 15 cores within that field, stirring those up good, and taking a pint of that as your sample. So with that said, good luck on your soil testing program.
All right. Evidently, it's really important to get the top 6 inches there.
That's a great video.
That's one of my favorites. So I'll continue now to the next slide and talk about soil test nutrient management. There are 20 nutrients that have been identified that are required by plants. Of these, nitrogen, phosphorus, and potassium are required in relatively large amounts. Nitrogen is associated with lush vegetative growth. Adequate phosphorus is required for flowering and fruiting, and potassium is necessary for durability and disease resistance. Calcium, sulfur, and magnesium are also required in comparatively large quantities. The other nutrients referred to as micronutrients are required in very small amounts. These include such elements as copper, zinc, iron, and boron. While both micro and micronutrients are required for good plant growth, over-application can be detrimental as a deficiency. Over-application of plant nutrients not only may impair plant growth, but may contaminate groundwater by leaching through the soil or pollute surface waters by washing them away. Home tests for pH, nitrogen, phosphorus, and potassium are available from garden centers. These may give you a general idea of the nutrients of your soil, but they are not as reliable as tests performed by a cooperative extension service at a land-grant university. Universities and other commercial testing services will provide more detail and you can request special tests for micronutrients if you suspect a problem. In addition to the analysis of nutrients in your soil, they often provide recommendations for application of nutrients or adjusting the pH. So with that, I will end with a couple of slides on soil health. Soil health has been a recent idea come up in the last 4 or 5 years, and it's started to get talked about a lot throughout the NRCS and other agencies. So when we look at soil health, we're looking at soil organic matter, nutrient retention, soil fertility, soil structure, soil stability, and soil erosion. The physical aspects of these are bulk density, infiltration, soil structure, micropores, soil depth, and water holding capacity. Chemical, we're looking at electrical conductivity, reactive carbon, soil nitrates, soil pH, and extractable phosphorus and potassium. Biological, we're looking at earthworms and microbial masses. Carbon and nitrogen, particulate organic matter, potentially mineralized nitrogen, soil enzymes, and soil respiration, as also total organic carbon. So, some soil health management ideas for you to think about. Soil works for you if you work for the soil by using management practices that help improve soil health and increase productivity immediately and into the future. A fully functioning soil produces the maximum amount of products at the least cost. Maximizing soil health is essential to maximizing profitability and productivity. Soil will not work for you if you abuse it. Managing for soil health is mostly a matter of maintaining suitable habitat for the creatures of the soil food web. This can be accomplished by disturbing the soil as little as possible, growing as many different species of plants as practical, and keeping living roots in the soil as often as possible, and keeping the soil covered at all times. So, soil disturbance can be the result of physical, chemical, or biological activities. Physical soil disturbance, such as tillage, results in bare and or compacted soil that is destructive and disruptive to soil microbes. And it creates a hostile environment for them to live. Misapplication of inputs can disrupt the relationships between fungi and other organisms and plant roots. Something that y'all probably won't run into, but overgrazing is a form of biological disturbance which reduces root masses, increase runoff, and increases soil temperature. All forms of soil disturbance diminishes habitat for soil microbes and results in a diminished soil food web. So how do we do this? Plants use sunlight to convert carbon dioxide and the water into carbohydrates that serve as the building blocks for roots, stems, leaves, and seeds. They also interact with specific soil microbes by releasing carbohydrates or sugars throughout the roots into the soil to feed the microbes in exchange for nutrients and water. A diversity of plant carbohydrates is required to support the diversity of soil microorganisms in the soil. In order to achieve a high level of diversity, different plants must be grown. The key to improving soil health is ensuring that food and energy chains and webs consist of several types of plants or animals, not just one or two. Biodiversity is ultimately the key to the success of an agriculture system. Lack of diversity severely limits the potential of any cropping system and increases disease and pest problems. A diverse and fully functioning soil food web provides for nutrients, energy, and water cycling that allows the soil to express its full potential. Increasing the diversity of crop rotation and cover crops increase soil health and soil function, reduces input costs, and increases profitability. So the bottom line is to keep its living root throughout the year. Living plants maintain a rhizosphere, an area of concentrated microbial activity close to the root. The rhizosphere is the most active part of the soil ecosystem because it is where the most readily available food is located. and where peak nutrient and water cycling occur. Microbial food is excluded by plant roots to attract and feed microbes, which in turn provide nutrients and other compounds to the plant, and at the root soil interface where the plant can take them up. Since living roots provide the easiest source of food for soil microbes, growing long season crops for a cover crop following a short season crop feeds the foundation species of the soil food web as much as possible during the growing season. Healthy soil is dependent upon how well the soil food web is fed. Providing plenty of easily accessible foods to soil microbes helps them cycle nutrients that plants need to grow. Sugars from living plant roots, recently dead plant roots, crop residues, and soil organic matter all feed many and varied members of the soil food web. Here are some ideas for a winter cover crop mix. I'm looking forward to trying some of those this year. So the idea, like I said, is to keep the soil covered as much as possible and keep a living root. The soil cover conserves moisture, reduces temperature, intercepts raindrops to reduce their destructive impact, and suppresses weed growth. That's my favorite part about a garden, is the suppression and weed growth. It also provides habitat for members of the soil food web that spend at least some of their time above ground. This is true regardless of land use. Keeping the soil covered while allowing crop residues to decompose so their nutrients can be cycled back into the soil can be a bit of balancing act. Producers must carefully consider their crop rotation and residue manage if they are to keep the soil covered and fed at all at the same time. So with that, there's a list of summer cover crops that could be tried out. And that's it. I got some references and questions. Discussion. Everybody might be asleep by now.
Oh, no. I found that very interesting. Thank you very much.
Chris, where can you buy one of the tools to take the soil samples here in Corpus?
Here in Corpus, I'm not sure.
I just ordered them online.
Okay, what would it be called?
To soil auger.
Soil auger?
Or a push probe, yeah.
Okay.
I think Ace Hardware on the island has them. I'm not certain of that, but I think I saw one there.
Okay.
I just go online and look for them is what I do.
I have several questions, but I'll let the students go first.
Okay.
Where do you send the soil samples around here?
The soil samples, what I just recently found out, the Texas A&M Extension office here should have soil sample bags available to pick up, and then I believe they go to College Station to the laboratory there for analysis. And I also heard the other day that Stephen F. Austin has a soil lab also.
May I comment on that, Chris?
Yes, please.
We accept soil samples on a regular basis. We have all the forms, all the materials, and all the directions on how to do it. And usually, as part of this class, we allow y'all to collect a soil sample and submit it. So,
yeah, the lab in Massachusetts.
If you want them, all you got to do is holler at me.
The lab in Massachusetts is only if you want heavy metal testing, like you have a post-industrial site you want to turn into a community garden.
Okay, thank you, Kevin.
What was the question? Was that for me?
All right, I have several questions. What was the tool you used to cut open the core samples?
A tool used to cut open the core samples. Was that back at the beginning?
It was beginning to middle. It was a core sample for like a semi-marine type of environment. Okay,
I really honestly do not know what that tool is. like I said, coastal soil survey is fairly new to me. And,
Okay.
I don't know what that tool is, but I do know that they say those cores, them samples that they cut in half are done after they cut it in half. It's a one-time use. So.
Huh.
Anyway, it's a pretty neat deal. I don't know for sure. Maybe I'll know next time.
How do people become employees of NRCS? I mean, do like people with PhDs go take a civil service test somewhere?
To be a soil scientist, it requires a 4-year degree and soil science type area. Our conservationists also have bachelor degrees at the minimum.
I understand, but does it like advertised in journals, or I mean, like how do you find out about openings?
Oh, all our openings are advertised on USA Jobs, usajobs.gov, and we have people all the way up through PhDs that are running the laboratories. We have PhDs in the field, and we also have people without degrees that work for us in the field and laboratories. So there's some of everybody mixed in.
Okay. You said it takes many years, many applications over several seasons to acidify a plot to desired pH. Once it gets there, you have to maintain it, right? So then you back it off to like once a year, or do you have to keep sampling?
So are you talking about adjusting the pH?
Yeah, like here we have a a lawn that's a pH of like 8.4, and you need to get it to like closer to a 6.5. The granulated sulfur, once you get it down to something reasonable, you still have to keep applying it. You just keep testing, or?
I like to test for your pH, like he said, every couple of years, every year until you get it where you like it. And then depending on the water, like if you're actually watering your yard, depending on what the pH of the water is, it may try to raise back up, and you might have to add a little sulfur continuously to keep it down where you want it to be.
Well, yeah, and the parent material is going to come back to dominate too, right?
Right.
Okay.
Yeah, it all depends on what it's made out of from the beginning.
Last one, I swear. I saved the most complicated one for last.
Okay.
So, you said that we have a vertisol, which means it's a clay that expands and contracts. I have friends that do pottery, and they said, well, you have to get a mineral clay. And then I talked to someone else who said, well, a mineral clay is one that comes from volcanism, but I was told by someone at the National Seashore that the reason our sand is so soft, that it's an ancient volcanic deposit. It's a volcanic ash. So what's the difference between a clay that's a clay by particle size and what my friend who does pottery is talking about as a mineral clay?
It probably has to do with the charges of the different clays, and to tell you the difference right offhand, I do not know. I do know that our soils around here is not related to ash. It's more, like I said, a marine deposit that settled out of the ocean. But
so the ranger at the National Seashore was wrong. Okay.
Well, there might be a specific spot that has some type of ash deposit that I don't know about. I'm sure there are some, but anyway, I'm not really familiar with the pottery clay to know exactly what they require.
We have a question from one of the students. Can we use vinegar to change the pH of our soil?
I don't know.
I can answer that.
Please do, because I'm afraid to.
You can use vinegar to drop the pH if you're putting on fertilizer or things like that, and it will temporarily drop the pH. But just like they were talking about earlier, it's great if you're trying to change the pH or grow acidic plants in pots, but it's not going to be a good long-term fix if you're trying to adjust the native soil.
And it'll kill some plants.
Well, you're not going to apply it like that, Beth. What you would do is get you some of the pH testing strips, and you would figure out what the combination of your injector system is, and you would apply the amount of vinegar to bring the pH down when it comes through the injector and injects out. It's very doable. It's actually not that complicated. You figure out, well, how much of a gallon of vinegar do I pour into my container of fertilizer so that when it comes out the injector, it comes out at the right pH. Do you agree, Chris?
That sounds great to me. Yeah, I can see where it could work.
We used to use it when I was out in West Texas, and the pH of the water was over 8, and we were having tremendous problems in the greenhouse, and we started playing around with vinegar, and we got it down to where the pH was 7.5, and we were very happy with it, and never had any issues of it harming any of the plants or anything like that. So,
Kevin,
I'm
I
gonna try
understand
it.
you're talking about those bottles that go on the bottom of your hose, and then you spray the whole thing, and you're constantly diluting it as you spray it. Like my dad used to use that to spray tent caterpillars back home.
no, I'm not talking about that. I'm talking about an actual fertilizer injector system where you mix up, where you you figure out your ratio, and it's usually like a 1:16 or a 1:15 ratio, and so you have to figure out how much goes into either the drum, or I always just used a 5-gallon bucket because my greenhouse wasn't huge, but that worked well. Is that what you're talking about, Ben?
I've never used an injection system. I don't know what an injection system is. I'm very hand tool.
An injection system pulls out parts per million and mixes it in with the water, and so it basically pulls the fertilizer out and injects it into the water as it's flowing through the hose, so that it comes out in a diluted. So you'll mix it up in a concentrate in the bucket source, and then it pulls it out in a diluted form once it's at the plant source or at the plant delivery.
I have one question about classifying soils. This is Tara. Mr. Hobbs, you were speaking about the different, like the vertisoils, the vertisols, the something. What did you say the type of soil we have here in Corpus or in this area?
A lot of them are the vertisols that shrink and swell and move. Yeah, the vertisols is what we have a lot of here in this area, I've seen.
Okay, and what about the slick and slides you were saying?
Yeah, there's down in the B horizons, the subsoil. If you dig a pit down in there and you pull the soil apart and look on the inside, there will be shiny pads on the inside where the soil actually moves and rubs together whenever it wets and dries.
Okay, and that, like, if I went out into my flower bed and dug down, and I've got the worst soil, I think, in my flower beds. So if I dug down and I saw that, I would know that I had an area that has a slick and slide in it.
Possibly another thing you can look at is whenever it's dry, the surface, there will be cracks in the surface.
My whole backyard looks like that. Really?
Yeah.
Tara, I had a slip and slide when I was a kid.
I didn't. I had a, what do you call those? A pogo stick.
I had one of those too.
I had one for not very long on the pogo stick.
Thank you very much for answering the question. Thank you.
Yes, any more?
Okay, well, thank you, Chris, for coming and presenting for us tonight, and I hope you all learned a lot. And Wednesday we'll actually have a soils lab and see what Deb Holiday has to offer us. So she and I talked today, and she's working on stuff. So
thanks for having me.
Thank you so much. Y'all have a wonderful night. If you hurry, you have enough time to make it to Walmart.
Thanks, Chris. I missed your props, but the videos were awesome.
Thank you.
Beth, if you want to learn how to use a fertilizer injector, I'll teach you, okay?
All right. Maybe after the vaccine.
Okay. Bye, y'all.
Bye.
Bye, Vince. Somebody wake Vince up.
I'm awake. I'm getting ready to sign you out.
Bye.
Do it, Vince. Bye.
Okay. I sent you the roster.
Okay.